Good morning and welcome to today's webinar, Measurement Risk and the Impact on Your Processes. My name is Sarah Wallace from Transcat and I'll be your moderator this morning. Joining us on the call is Howard Zion, Transcat's Director of Technical Operations, Jeremy Sims, Transcat's Supplier Quality Analyst, and Dan Colvin, Wind Energy Account Manager with Transcat. Today we will spend the first part of our time in presentation and then end the call answering your questions. Anytime during the presentation, you can send questions through the question box to the right in your webinar controls. If we happen to run out of time before getting to all the questions, we'll follow up offline to the email or phone number you provided at registration. I also want to mention the webinar is being recorded and will be available for viewing through transcat.com. At this time, I'm going to turn the presentation over to Howard.
Thank you, Sarah. And thank you to the webinar audience for taking your valuable time to listen to some of the concepts that I think would be useful to you. And hopefully it will stimulate some thought on how this can help you in the long run. Let's get started. We're going to cover a few concepts today, and these are only conceptual. I'm not going to go into any detailed examples in this presentation. We'll talk about what measurement risk is, how risk creeps into your manufacturing process, how it can creep into the calibration process, and then the calibration results and the impact that has on your manufacturing process. And then, as Sarah said, we'll get into questions and answers. So measurement risk is a probability that the instruments you're using and making decisions upon for your product are not what you think they are. That maybe those instruments are incorrectly influencing that acceptance decision of your product. So if you're accepting bad product, that can lead to negative results ranging from simple consumer dissatisfaction to something more extreme like fatalities and lawsuits. But if you're rejecting good product, that can lead to negative results as well, possibly unnecessarily scrapping work, parts, components of your product, or reworking those components of your product, and that's wasted resources, as well as evaluating out-of-tolerance results and having to use your resources for that function. It's possible that some of your rework, scrap, recall is related to the result of unbridled measurement risk, and you may not even know it, you may not realize it. So how can you determine if measurement risk is a problem in your manufacturing process? Let's flip that around and talk about, instead of measurement risk, talk about measurement assurance. Measurement assurance encompasses a number of assumptions in your manufacturing process, and I'll list 10 of these. The first one is product acceptance. Did you make the right decision about the acceptance or rejection of your product or a component of your product while you were in the manufacturing process and in your quality acceptance process when you were using instruments to make that decision? The basis of that decision is the instrumentation that gives you the quantitative values. Suitability for intended purpose is making sure that you've selected the right instruments for making those decisions about your product acceptance. Instrument application has to do with using the instrument correctly. You may have selected the right instrument, but are the things that you're doing that cause errors in the measurements? A term that I call beginning of period reliability, and that is the calibration of the instrument prior to using it in your production process. Does it meet its performance expectations prior to you putting it into the place? And then the end of period reliability is at the end of the calibration cycle, that subsequent calibration, and does it indicate that there was any error in the instrument when you were using it to make decisions about the process? And then the calibration process itself. Were those calibrations executed correctly? And I'll go into more detail of that in a few minutes. Following the calibration, your non-conformance review. If your instrument failed to meet its performance specs, then your quality system probably has a review process in place that evaluates whether that had an impact to the decisions being made about the quality of your product. because that changes the quantitative values that you're relying upon. And then the accuracy of that nonconformance review. How thorough is it? Did it miss the mark on making sure that it, evaluates whether those errors in the instrument actually had an impact on where it was being used? And then risk mitigation. Any negative result from the impact study and how that's mitigated to remove or reduce risk in your product. So if you put a value on each of these 10 areas for measurement assurance and scaled that from a 0 to a value of 1, you could come up with the total overall health of your measurement assurance program in your production process. And you do that by multiplying the values together. And that's kind of like a reliability figure. So it would be 100% if each of these were at a value of 1. I've given a few examples here of how that might change. For example, if all of the areas had a value of 1 assigned, but the instrument application indicates that in some situations it's being used incorrectly. You have the right instrument for the job, but there's something your personnel are doing in the process that cause errors, and you evaluate to figure that this has a value of 0.95. And also that your accuracy or thoroughness of your nonconformance afterwards, when you find out that you have an out-of-tolerance condition, isn't as thorough as it needs to be. Let's say you give that a value of 0.9. Your overall health would be 85 or 86%. In the next example, for example 2, everything is good except for the calibration process where, for example, half of the test points were checked based on where the instrument is being used and how it's being used in the process. So if you didn't check all of the functions or all of the ranges of an instrument where it's being used, you've lost traceability in your measurement. You have no idea about the confidence of your measurement. So let's say half of those are being checked, you give that a value of 50%. Overall, it drops to 50%. Example 3, reliability would say that you don't have an NCR review process at all. I've seen situations like this, although it's not very common. But that's the point of the whole traceability chain of measurement, is not only to make sure that you have equipment that's suitable for the intended purpose, but make sure that you're using the end result of the calibration of those instruments to determine whether you have an impact to the product. And if you're not reviewing the results of those out-of-tolerance conditions, and in some cases intolerance conditions that are close to the limit, then you're not doing yourself any favor. You're throwing away good money for the calibration process and the use of the instrumentation to control your process. So I want to talk about some specific categories here, starting with suitability for intended purpose. Again, when you're looking at selecting an instrument to make measurements in your production process, you've got to take a look at the parameters that you're measuring in the process and make sure the instrument can measure those same parameters. You also want to make sure that you have a good, accurate product that can make stable measurements for those readings. What environment is it being exposed to? You've got to check that as well as part of the suitability for intended purpose, making sure that the instrument, as stated by the manufacturer, can work in the environments and that it's being used in, and that you're checking also to see if there's an impact to its accuracy based on the environment that you're exposing it to. And then the other thing is the experience of the operator and their ability to use the instrument properly so that you don't introduce other errors in your measurements. The application, and that's what that leads to, is the correct use of the instrument. Incorrect use can introduce the errors that can cause you to have a different outcome of your decision whether the product's good or bad. A few examples here. If you have a platinum resistance thermometer with an indicator, the way that has to be used is that during the calibration there's a set of coefficients determined that have to be programmed into the display. There are some types of connectors where that's automatically programmed into the connector and it removes the operator error. Some of the older units have that, though, where you have to enter the coefficients into the display. And if that is left at the old coefficient values, or the wrong coefficients are plugged in, or the probe is changed out without changing those coefficients, you're going to get incorrect temperature readings, and you're going to make wrong decisions about your product or your process. A set of calipers. Those are easily picked up and moved around and possibly dropped, and if you have nicks or burrs on the jaws, that's going to shift your zero or possibly affect your readings. Torque wrenches. Without having any damage to the instrument at all in its normal use, there's enough influence from how the operator uses a torque wrench that you can introduce up to 10% error in the reading. And a good gauge repeatability and reliability study would indicate how much error you have. Drive block calibrator is another good example. There are so many different types of influences an operator can have in not transmitting the temperature properly. From the wrong size insert for the temperature probe being used, to not compensating for axial uniformity, which is from the top to the bottom, versus radial uniformity, which is from well to well. Overloading it, putting too much into it, can cause the temperature transfer to be incorrect. So you may think you're generating a certain temperature from a drive block calibrator, and you're not actually getting that. And that introduces error, which changes the result of your testing of your product. An oscilloscope, for example, if you're using it above or near its bandwidth limits, can cause a frequency cutoff for the amplitude, and you get a different reading than you think you're getting. And again, you're making decisions based on that for your product or your test of your product, and that can change everything about whether you call that good or bad. Beginning of period reliability. Here's some things to think about. When you purchased the instrument initially, did you put it right into production without having it calibrated first? Did you rely on a production cert, which is not always a guarantee that it meets all of its performance specifications? Was the initial calibration 17025 accredited, which brings a lot of detail behind that? We have some white papers on that if you don't know the details of 17025 accreditation. Many times OEMs are not accredited. And then when you recalibrate the instrument, was it returned to you in a condition that was maybe close to the tolerance limit? How long will it maintain that condition through its next cal interval? So those are some of the things that you need to think about that can cause nonconformance reviews to occur, which cost you money. End of period reliability is the most critical information you can have, because now that you've used it for that calibration interval in your process to make decisions about your product, here's the final result that tells you how it performed, how that instrument performed, whether it maintained its tolerances. Was it found to be out of tolerance, or was it in tolerance and close to the out of tolerance limit, which can still have an impact on your decisions about the quantitative values that it provided. And then this gets into the lab's uncertainty, measurement uncertainty, and how this impacts that close to being out of tolerance region. How do you use this information to determine how it affected your product or your decisions about the product or tests that you ran during the last calibration period? Now let's talk a little bit about the calibration process and where things can go wrong there. What are the measurement parameters, the functions, ranges of the instrument you're submitting for calibration? Does it have multiple ranges, multiple readings, or is it a single-use instrument? Then you have to get into the accuracy of those ranges or values or of the instrument to determine what you think the tolerances should be for acceptance. This is what you or someone in your organization should have based a decision on when you selected it for the suitability for intended purpose category. You base that likely on what the manufacturer stated it will meet. Sometimes you'll change that to what your tolerances are required to meet for your production process. And then you've got to look at the lab that you're sending it to, whether it's an internal lab or an external commercial lab. Are they capable of measuring in those parameters or those functions or ranges or values. How does their measurement uncertainty compare to the tolerances or the accuracy that we talked about above of the instrument? Will that lab be able to provide valid results that are meaningful to you? If their uncertainties are as large as the tolerances of the instrument, is there any value to that? Certainly their uncertainties need to be significantly smaller. And what test points will they check on your instrument? We've seen examples where a calibration for, let's say, a temperature indicating device that had 2 channels and 4 different thermocouple types on each channel was only checked on 1 channel and 2 thermocouple types, yet the instrument in the production process was used on both channels and 3 out of the 4 thermocouples. There's no traceability for the channel that wasn't checked or for the other thermocouple types that were not checked, and therefore they have no control over their measurement process. They have no indication whether that meets or does not meet the tolerances of the instrument, and that's the basis of their use of the instrument in their process. So it's not capable of producing valid results if it's not being checked. So getting down to the tolerances that are applied in the calibration of your instrument, are those the same as the ones stated by the OEM? Or if you decided to change those tolerances for your purposes, does your calibration provider know that? And did they apply that to your calibration? Changing those tolerance limits changes whether or not you're notified that it's in or out of tolerance, in or out of the correct tolerances. And if you're not being notified when you should be, because those tolerances are different, then you're missing evaluations on whether there was an impact to your product. The reverse is also true. If those tolerances are tighter, you're being told to perform a nonconformance review when you probably don't need to, and you're wasting resources. So it's very important that you ensure that those tolerances are correct, not just looking for out-of-tolerance conditions, but especially initially when sending an instrument to a calibration provider. First time you get that back, check those tolerance limits, make sure it's what you expected it to be. Another thought process for the calibration of your instrument is whether the technician is competent to perform the calibration. How do you know whether they're competent or not? And this is really part of what 17025 brings to the table. And then in the end, is the calibration report that you receive easy to understand, or is it difficult to read? Does it give you the information clearly? Or is it something that you're searching for the right information and not really quite sure how to read it? So let's talk about the end result. Assuming that the calibrations perform correctly, the tolerances are right, all the test points are there that you need, good technician performing the calibration, competent for the measurements. Now you get to evaluating the out-of-tolerance results and performing a nonconformance review. Whether or not your quality system mandates that you do this, doing so can help prevent safety issues, can save you money, costs, can prevent negative marketing of your product if you're getting bad results. The evaluation is often under-executed from my perspective and my experience, resulting in a false perception that there's no impact to the product. If these NCR reviews are not thorough enough or not checking the right, making the right comparisons of the out-of-tolerance data to your decisions, or not capturing all of the areas where the instrument was being used, that's often a problem, then you're effectively breaking the traceability chain or breaking the measurement assurance process for your product. And again, the whole purpose of spending the money and selecting the right instrument and getting it calibrated and getting the results is so you can evaluate that everything was good. And if it wasn't good, you can mitigate that risk. We offer consulting in this area to help your engineers and quality personnel understand how to get better value out of those impact evaluations, those NCR evaluations. One general question to ask yourself is how many of these evaluations have you had in the past 5 years, and of those, how many had a negative impact on your product? If it's near zero, or it is zero, what's the probability of that? Does that seem right? What's your gut feel? Is there possibly something not being done correctly in your NCR review? And maybe you should dig into that. If it seems too good to be true, you might consider the quality of the evaluations being performed. And if you don't do it, an external auditor might. And they may not see it the way you do, saying that you are error-free. They may say, you know, you've had an awful lot of these evaluations, and you've either got a very good quality system in place to prevent any impact to the product, or something's not right about the process. So then you get down to the risk mitigation, and that is when you've determined that there's an impact to the product, what do you do with that information? How do you make sure that you fix the problem in your process? Make sure that that instrument is either changed out if you have a reliability issue with it, so you don't have those impact studies that you have to do that cost you money, or more directly, whether that out-of-tolerance data had an impact on your product being called good or bad in the past calibration interval. If it caused you to reject good product, it's in your best interest to determine how much it cost you in scrap rework, scrap product rework, or the NCR evaluation costs. If you ended up, as a result of the outer tolerance, accepting bad product, it's in your best interest to chase that down as well, because accepting bad product and putting it out for your consumers to use can cause a perception that there's a problem with it, a faulty product. You could end up with liability suits that are related to this. You could have property damage, medical costs, fatalities. Hopefully you're not to that extreme, but you certainly may have some costs out there that are unnecessary. So you want to get to the root problem and reduce or prevent these from recurring. In the end, your business is not just about guidelines and having to meet requirements. It's about making a safe and reliable and superior product that fills a need in the market and becoming profitable at doing so. Having errors in your measurement process can cost you money and reduce your profitability. Your measurement assurance program should be designed to help you minimize the risks in your processes and your decisions about the product, about its safety, about its quality. Too often, one or more of these categories that I've mentioned are not fully implemented. And that, again, causes the reliability of your measurement assurance program to lose value, to become ineffective, or for you to waste money on something that's not being implemented fully. If you're going to put the effort and the money into some parts of this, why wouldn't you put it into all of it? Make sure that it doesn't impact your cost. Make sure it doesn't impact your profitability. Make your measurement assurance program robust so that it keeps you away from the costs or from negative safety issues. Thank you for joining us today, and I'll pass it over to Sarah for questions.
Thank you, Howard. Before we move on to the question section, I just wanted to mention that the white papers that Howard mentioned on the call or during his presentation are available on the technical resources section of our website. And if you want more information on that, you can just email me and I can give you specifics. Okay, just as a reminder, if you would like to ask a question, just send it through the question box in your webinar controls to the right. So we will move on to our first question. Okay, how can I fiscally justify this to my supervisors? Howard,
that's a very good question. You know, we actually talk with our clients about this fairly often, and if you take a look at the cost of your calibration compared to your overall cost of the business, and the impact that can have to the cost on quality, to scrap, reworked, or recalled product, or simply by evaluating what it costs you to do a nonconformance review. That's probably the easiest number to get to. because it's a little bit more difficult to determine whether you had scrap or rework based on out-of-tolerance conditions, although you can do that. So the first and the low-hanging fruit I would go after is the impact of your out-of-tolerance evaluations. How many of you had, and what does it cost you per event? What is the time consumed for each of the individuals involved? And what we've discovered from our pharmaceutical and medical device customers is that this is anywhere from $5,000 per event up to $25,000 per event, depending on the product line. That can be very expensive. So first thing would be to get that understood so that you know how much that cost you, and then multiply it out times the number of non-conformance reviews that you've done. That should help you to justify investment in a better calibration program if that's the cause, so that you can reduce those costs.
Okay, thank you. The next question is, do you offer 17025 calibrations without uncertainty?
We currently do. That's been a point of debate. ILAC has put out a notification that uncertainties are to be provided with all accredited calibrations, and that's not yet been enforced. It's dependent on the accrediting body at this point. Right now we're accredited in all labs by NAVLAP, and NAVLAP has not enforced this fully yet. It may be coming, but we're waiting on a decision. And I think the question goes back to the wording around this subject. And it comes down to a simple and/or in one of the statements that says you can interpret it one way to say you must provide uncertainties with every reading, versus as long as you're giving the tolerances to the client, then you don't have to report the uncertainty. So that's the debate. And so we're waiting for a result of that. In the meantime, all of our calibrations are accredited regardless of service level. The service levels that we offer are CERT with data and uncertainties, CERT with data only and not the uncertainties, and then certificate only if you don't want the data. Although I do not recommend that level of service because you're not getting the information you need to make decisions about whether your tolerances were correct, out-of-tolerance information that you need to evaluate out-of-tolerance indications and non-conformance reviews. But those are the service levels that we currently offer, and that may change in the future.
Okay, thank you very much. We have had a few people ask if they can get copies of the presentation. We will have the recording up online, and I can also make the slides actually available as well. So just in case anybody else is wondering, we'll send those to you in follow-up emails after, probably next week. Next question is, how can I implement an equipment risk evaluation within our measurement program?
Equipment risk evaluation. Part of that would be to take a look through CalTrack Online. We offer for the calibrations we provide, or for the calibrations that our clients have us send out to vendors for the measurements we can't make. That information is all on CalTrack Online. And if you take a look at your instrument inventory and the results of the calibrations over a period of time, you can take a look at how reliable those instruments have been as a basis for changing your cal intervals or changing out equipment altogether. That's one way to go about it. Another thing would be when you see a high out-of-tolerance situation for a specific model or a specific instrument, take a look at how it's being used in your process. See if there's anything in your process that's influencing that to become out of tolerance. That's a possibility as well. We've seen that on occasion with clients. And you can reduce that liability of out-of-tolerance situations by perhaps implementing a change to the process where it's being used.
Okay. Next question is, do you see one type of error over other types of errors?
You know, the thing of those 10 categories, I assume that's what we're talking about here. It's surprising to me how often an instrument is not selected correctly for suitability for the intended purpose. One of the things that I always ask a client when they're talking about an instrument is, what are you trying to do with the instrument? Where are you using it? What are the production tolerances or the testing tolerances that it's being used against? Start with that. Understand where it's being used to make sure that suitability is correct, and make sure that that instrument is capable of producing valid results for that type of measurement and for those tolerances. So that's one area that I'm a little surprised that I see problems with. And then another area is the calibration process itself. You know, without throwing any of our competitors under the bus, we see partial calibrations being done that are not identified as being partial calibrations. And traceability is lost for those clients, and that seriously impacts their quality, and they may not even realize it. I think they're getting a good calibration, and maybe they're not. So that's a big problem that needs to be monitored, or the watchdog has to be the client. It is the responsibility of the calibration lab to perform the calibration correctly. And unfortunately, there's not enough personnel or resources in these accrediting bodies for accredited labs to be the watchdog for that. They rely on the customers and or other labs to report situations that are not correct. Those are the two biggest areas.
Okay, great. Another question is, how can Transcat, I think it's judge in-out tolerances without uncertainty?
All of our accreditations are, all of our calibrations are accredited. We have uncertainties for every one of those readings, whether we report them or not. And we actually have a new tool that we've developed and have put into place so that our technicians can see when they're performing the calibration. That is called the Probability of Compliance to Specification, or PCS tool. That allows them to understand where they are relative to the tolerance limits and our uncertainties. So that information is being used and is available at all times, whether the client receives that information or not.
Okay. Next one is on certification. What does certification tell us aside from functionality?
I assume certification meaning the calibration process. The calibration provides the traceability to SI units up through the traceability chain. Maybe reword the question if I missed the point there.
Okay. Well, we're waiting for that. When do we decide to adjust the equipment when it is near limit of tolerance?
That's a very good question. We're in transition at this moment because that PCS tool that I mentioned is something relatively new that we've developed. And right now, our standard practice is to adjust at 75% of the limit. Now, typically, if you're at a 4-to-1 test uncertainty ratio, or TUR, 75% would be the adjustment limit so that you're not into the guard band region. If you're not familiar with these terms, I recommend that you read our K = 3.9 white paper on our website. So the PCS function that we have, or feature that we have in CalTrack for our technicians, is there to allow them, when they have the uncertainties, to see where they are into that guard band region. And if they're into the guard band region at all, regardless of the TUR, that's when they'll make the adjustment. We do not optimize unless the customer asks us to optimize, meaning adjusting every time the instrument comes in, regardless of where it is. Again, that's a specific request. We don't want to do that because if customers are trending their data, that would interrupt the trend. So if they have it in a control chart or something like that. So again, that's a client request to optimize. Otherwise, we adjust currently at 75% unless we're reporting uncertainties, and then we adjust when it's in the guard band. And that will likely be changing to adjustment in the guard band at any time. We're in the process of putting that into place.
Okay, excellent questions.
Very good questions.
Yeah. Which is more accurate for pressure, analog or digital?
Well, it depends on the resolution. Obviously, with analog gauges of any type, you are interpreting. It's more open to subjective error. With digital gauges, you're going to be dependent on the resolution of the instrument as well as the toggle point for the next smallest digit to increment or decrement. So obviously digital gives you an advantage in that regard.
Okay. What would be a good way to determine an appropriate calibration tolerance for a given test point?
Calibration tolerances should always be compared, regardless of how they're determined, should always be compared against the test that the instrument is being used in. Those tolerances for that process are really what should drive that. So you want to have a good ratio there. It's no different than when a Cal Lab performs a calibration on your instrument to the tolerances, and their uncertainty has to be a relatively small relative to those tolerances. Same thing with using the instrument in your process. That accuracy or tolerance of your instrument needs to be relatively small compared to the tolerances you're trying to measure in your process. Pretty well standard for the industry is a 4-to-1 ratio. Then you get into whether you call that a test accuracy ratio or a test uncertainty ratio or a process accuracy ratio in this case versus a process uncertainty ratio, because there are other components besides the accuracy of the instrument that can influence where you are in that tolerance window for the process. So you really need to look at your uncertainties in that process, and I know most industries don't go there yet, but they really need to, and certainly those same concepts that we apply in the calibration lab can be applied in process measurements as well.
All right, here's another question. We keep getting lots of them, which is great. Keep them coming, because if we don't get to them today, remember somebody will follow up with you after the webinar with an answer. What do you charge for making adjustments?
Our standard practice currently is that we do not charge for adjustments. There are a couple, and I mean just very few examples where we would charge for adjustments. One of them being when we have to refurbish weights, which is really adjusting the weight value because you're stripping it down, cleaning it, and then repainting it. So we do charge for that type of a thing, but for the majority of instruments, we do not charge for adjustment. That's built into our price.
Okay. To keep costs at an acceptable level, is there a general accepted process to determine calibration cycles?
Our NCSLI has recommended practices, a series of recommended practices. RP1 is all about adjustment of the calibration intervals, and there are 4 or 5, maybe 6 methods there, from very simple to very complex. There's also a company called Integrated Science Corporation that sells software for you to help you determine some of the more complex calibration interval adjustments. But RP1 is a good place to start, and taking a look at that at ncsli.org.
Okay, we did have one person ask if Howard was going to be presenting a white paper at the NCSL show that's coming up here, I think in 2 weeks.
Yeah,
Howard, you're not presenting this year, right?
Coming up pretty quick. I am not presenting this year. In fact, I don't think Transcat has anyone presenting this year.
No, but we will have a... Oh, I'm sorry, go ahead.
I will attend, myself, Keith Bennett, our Director of Metrology. We have a new person on board, Ken Cole, who will be there as well. And then, of course, some marketing and sales people.
Yeah, our booth number is 225. So stop by and say hello to the Transcat people while you're there. Another question we have, does the cert we receive from a third party tell us that the equipment is now calibrated according to the manufacturer's specifications?
If the calibration was performed to the OEM specs, I can speak for Transcat that we show you the as-found readings when we received it, and then if there's any adjustments or repairs made, we do that and we annotate that, and then the as-left readings are reported as well to show that it meets the tolerances that were given to us, whether those were the manufacturer's tolerances or your specific requirements. Those are stated on there. Now, on our cert, on the header, it will tell you at the top, calibrated to, and it'll say either manufacturer specifications or it'll say customer specifications. So it'll be clear on the header, at least from us, which ones were used. And then again, another place where if it's calibrated to the manufacturer's specifications, another place that those tolerances can go wrong is if the accuracy specification stated by the OEM, which can be very complex in some situations, is interpreted differently by the Cal Lab than it was by the person making the decision in your process that it was the right instrument. You can end up with different tolerance results because you have to convert those accuracies to tolerances. It's another good place to look to make sure prior to sending it in that that's correct, if that's a complex area. There's a lot of instruments that just have simple tolerances from the OEM, namely dimensional gauges, things like that. Those are pretty straightforward, but you get into RF microwave equipment, frequency counters, signal generators, things like that, that can get pretty complex. So I would recommend that you actually check that out, make sure that's what you expect it to be, so that when you get the cert back and it says calibrated to manufacturer specifications, you are assured that those tolerances are what you expect them to be.
Okay, we have time for one more question. To keep costs at an acceptable level, is there a generally accepted process to determine calibration cycles?
I think that's a repeat of one or two of the previous questions. And again, looking at RP1 would be the place to start for calibration intervals. And it helps you to determine, based on the instrument's history, where that calibration interval should go. Now, there's also a paper written by David Deaver, who previously worked for Fluke. He's retired. And I forget the name of the paper off the top of my head, but it was a good paper that really brought together a lot of different variables for the entire life cycle of an instrument, from the initial cost of the instrument to the repeat calibration costs to the cal intervals to a number of other factors. And that paper really got into the details of how you make that optimized for cost and safety for your process use. Very good paper.
Okay, we'll actually squeeze one more in before we wrap up. Is there a risk when using an OEM for calibration?
Yes, there is. There can be. There are some OEMs who are very good at metrology as well as manufacturing products. There are some OEMs who have no idea what metrology is and what traceable measurement is, and it's obvious when you look at either their lack of a calibration procedure or the fact that they call an adjustment procedure a calibration procedure, and they start right out by adjusting the instrument without preserving as-found information. And that as-found information is critical to you determining whether that decision process during the last cal interval was good or bad. So I would say that use that with caution. A lot of people jump to saying, well, the OEM's the expert, they should know best, and that's not always true.
Okay, thank you very much, Howard, and the rest of the guys there on the call. Thank you for your help with answering questions behind the scenes. I just want to let you guys know that the webinar recording will be available. If it's not available on the Transcat website, because I think somebody let us know that they were having a little technical difficulties, they are on YouTube on the Transcat channel, so you can check those out there. And we also have some product demos up there in case you're interested. And also, we will send out a follow-up next week with the slides so that you'll be able to have a copy of those for future use. So if you have any other further questions or like to find out more about Transcat service offerings and the products we distribute, you can contact us at 800-828-1470 or on the web at transcat.com. The thank you for joining us today, and we hope you found the information on measurement risk useful and applicable to your job. Have a great week.
Thank you very much.